Okay, so this is a joint work with my supervisor, Professor Libre from Université Libre de Bruxelles, Raffaele Presenti from Università di Venezia in Italy, Juan José Salazar González from Universidad de la Laguna in Spain. And yes, I want to propose some mixed integer linear programming models, so for short MIP models, to estimate phylogenies under the minimum evolution criteria. The term minimum evolution, maybe it is not really is an epi, because it can refer either to the parsimony criterion or it can refer, for example, to the distance-based methods. Specifically, I refer to the distance-based methods, so to avoid any possible misleading. And maybe it will be clearer in the following presentation. I want to start from the beginning, from and in particular from this picture that is in the seminal work of Cavalli Sforza and Edwards. The author observed that evolution over time can be described by means of a tree in which hedge split has population divergence. In this context, the limiting population can be considered as the intersection of the tree with the now plane. Typically, our knowledge about evolution is restricted to the now plane because we have a photo, a picture of the DNA sequences. We don't have a sampling of this picture over time. So that with this kind of data, the author assessed that we may be only able to recover not the real evolutionary process, but the projection of the real evolutionary process on the now plane. The author proposed also several models, namely a first maximum likelihood model, and then the minimum evolution model and an additive model. Let's focus on these two. The minimum evolution model they proposed was actually the first parsimony model. And the author said, well, if we consider some kind of molecular data, in particular they consider protein sequences, and if we assume that in the for the set of taxa that we are considering there is any problem of convergent evolution or reverse evolution, then in this context the shortest length projection can be considered as a good proxy of the real evolutionary process. Then they considered also an additive model in which differed from the minimum evolution model for the fact that on each edge of this tree, the process is considered, the evolutionary process is considered independent, and the distance observed by any pair of taxa can be considered as the sum of the number of mutation events necessary to transform one sequence to another. This, this criterion was then ported inside the distance matrix method by, I try to pronounce this, Reski and May, by this author, in their seminal works in 92, 93, and 94, in which they say, well, if we have unbiased estimate of the observed distances, then the real evolutionary process has a length that is, and so the projection has a length that is the shortest, as short as possible. And so they proposed some models that I try to summarize. Let's consider this alpha critical graph, an unweighted graph in which we have 2n minus 2 h. The h indicated with numbers means internal ancestor, represent the internal ancestor, and form a clique, so a full connected graph. And from each ancestor, I send an edge to each possible taxon indicated as a literal, so A, B, C, D, and so on. So I have a fan from each internal ancestor to the edge. On this graph, I want to find a weighted spanning tree. So the graph is unweighted. I want a weighted spanning tree in which each internal vertex has degree 3, and in which the length, the sum of the edge weight is as short as possible. In mathematical programming terms, this can be translated in this convex optimization program. If I indicate with WE the generic edge weight associated to the edge of my phylogeny, I want to minimize the sum of the edge weight, so the length of the tree, with the condition they proposed the additive model, so that for each path from a taxon to another, the distance that I observe must be equivalent to the sum of the edge weight belonging to the path. This problem is easy, which means that this can be solved in a polynomial time, when the distances observed are ultrametric, and the solution is the UPGMA algorithm. The problem is still easy also if we impose some relaxed constraint of the distance. For example, if they are just additive, and the solution is obtained by the algorithm showed by Butterman et al. That is called sequential algorithm. In general case, however, this problem is horribly hard, and the problem is that the solution, the optimal solution that we can get, that we may get, may not satisfy the obvious condition that the edge must be positive, the so-called positivity constraint. There are many articles that try to solve the problem inside the so-called least square models. For example, they are typically based on a Lagrangian relaxation of the positivity constraint. But while reviewing the literature, I discovered two very interesting articles, very old and practically forgotten by the literature. Well, that was proposed by Bayer et al. And Waterman et al., the first one and the second. They observed that if the distances must be measured in the same unit, then distances must define a proper matrix, and in particular, the triangle inequality must hold. By combining the triangle inequality on all the possible edge weight, we obtain that the sum of the edge weight belonging to the path from a taxon to another must be greater or equal to the distances observed from taxon I to taxon J. And in particular, each edge weight must be greater or equal to 0. So it must be a positive quantity because it represents a number, an expected number of mutation to transform one taxon to the other. What does it mean to represent, to model the evolutionary process by means of this model? If we admit, and we can always admit, that the evolution proceeds from a taxon father to a taxon child by a local minimal path, well, why local and not absolute minimal? Because, for example, selection cannot be constant during this evolution from taxon father to taxon child, and also because the allele that we will be selected from are not necessarily the minima that and so we don't have an absolute minimum from father to child. We have a local minimum, and typically local minimum do not combine to form an overall minimum. To model evolution by means of this model means to find a lower bound on the overall number of mutation happened during the evolution of the taxa analysis. The author, in particular, did not really solve this problem, this linearizable they just taken some possible phylogenies, some possible, well, alternative phylogenies, and they just solved the linear programming problem. So they try to estimate by means of linear programming the edge weight associated to each edge of the phylogeny. What I want to solve here is this problem. I want to find the phylogeny and the corresponding vector of edge weight, which minimize this function. This constraint is nonlinear because x is a variable, means the topology, the given phylogeny is defined, and w is either a variable. So it is not linear, but can be easily linear. We will see how to do it. I just tell you that currently I'm unable to solve optimally more than 12 taxa, but it is not really a big issue in this moment because I want just to present to you the models. Then we will, next episode, we will see how to try to improve the results. Well, maybe people working in combinatorics know that a phylogeny can be always represented by a particular network matrix that is called APT matrix, which means edge path incidence matrix over G. This matrix is made in this way. Each row represents a path from taxon I to taxon J, and each column represents an edge. So, for example, if I have this edge, it is 3, and I want to go from A to B, I have to pass. I have to cross edge EA. I have to cross edge E12, and I have to cross the edge 2B. So I will have in correspondence of the path AB, 1 in EA, 1 E12, 1 AB, and 0 elsewhere. This matrix is, the dimension is n times n minus 1 divided 2, where n is the number of spaces, and the number of columns are 2n minus 3. So it is relatively big if n start to be great. But imagine that I want to solve this problem. What I have to do, I have to try to assign at random the entry of this matrix. Then I call an oracle and they say, oracle, is this matrix representing an APT matrix? And the oracle say, no, this is violating some constraints. So I retry to assign at random the entries until I don't get a phylogeny, and then I try to solve the linear programming problem. It is a chaos because not only I have to solve the 2n minus 5 double factorial, I have to possibly enumerate the 2n minus 5, but I have also to consider that a huge number of my random trial assigning 0, 1 in the matrix are not representing phylogenies. So it is not a good idea to proceed in this way. So what a possible idea is to impose a lexicographical order on the column of my matrix. What does it mean to impose a lexicographical order? Well, if I have to go from the leaf A to a leaf B, for sure I have to cross from the edge attached to A, and for sure I have to cross the edge attached to B. So independently by this internal structure of this tree, I will sure have 1 in the edge EA and 1 in the edge AB. Which means that I can imagine that I can order all the columns in some way so that the first n column represents the external edge, that is the edge in which an ending point is a taxon. So something like this. And a yellow part that represents, for example, the internal structure of the tree. So how these are arranged. So, for example, the edge 1, 3 and the edge 1, 2. It is possible also to impose a lexicographical order on this part of the matrix, but it's quite complicated. I don't want to enter in the mathematical detail. But maybe I can. This is already good because I can remove all this column of the matrix. Why? Because this is constant. I mean, I always, whatever is the topology that I can enumerate, I will pass in any case from the external edge. So this is redundant information. But maybe I can make something better. Actually, if an edge k belongs to the path from taxon E to taxon J, this means that either k belongs to the path from A to EI, or it belongs to the path from A to J, but not both. This means that there exists a XOR relation between the row on my matrix. What is XOR? Is if I have a Boolean formula, if A is 0, B is 0, the XOR between these two entities is 0. Otherwise, it is 1 if one of the two is 0. Else, if both of the two are 1, I have 0. So look what's happened. I have to go from A to B, and I cross the edge A. I have to go from A to C, and I cross the edge EA. But if I want to go from B to C, I don't have to cross the edge EA. Actually, the XOR between 1 and 1 is 0. If you observe the row indicated in the red matrix and in the book, which is a green matrix, they are can be exactly obtained by this XOR relation. This is already great because I can remove more than the 75% of the entries of my matrix. But still, I have the problem of assigning the yellow block, which represents the internal structure of my matrix. And then we have a very nice theorem determining this. Before saying what the theorem says, which are the conditions that the entries of my matrix must respect so that the assignment, 0, 1 assignment represent a tree? Well, I have to assure you that there are no cycles, because a tree is an acyclic graph. The network that I'm representing is connected, and then the degree constraint is respected, because I want each internal vertex must have degree 3. So, if I have a matrix, or maybe it's better to represent. If I have a matrix like, I don't know, take the M2, for example. M2 means that for any possible combination of row and column, I pick up at random a row of 2 rows of the matrix, of this matrix yellow, and any 2 columns on this matrix. And I suppose that I obtain 0, 1, 1, 1. This means that I can go, as some I have the edge k, as some, for example, the other column is representing the edge k plus 1, and then I have the row q1, q, and then q plus plus 1. And I have the 0, 1, 1. This means that I can go from leaf A to the, I don't know, the leaf q by crossing not the edge k, but just the edge k plus 1. So this means that I'm already here, and I go in the edge k plus 1. Then, if I want to go from the leaf A to the leaf q plus 1, then I have to cross the edge k and the edge k plus 1, which means that I have something strange like this. Because in any case, the 2 paths pass through the edge k plus 1. This means that I have a cycle. And I can have only one cycle because the number of edges is fixed. I have only 2n minus 3 possible edges that I can choose. And I remove it, and then I have the remaining n minus 3. So I can always only have structure of this type. So if I have matrix of this type, this is not a tree, and vice versa. The second condition just say that the number of 1 on each column of the yellow matrix must be at least 2. Why? Because if I have some column in which the sum of the one is just 1, this means that I arrive some way along my path to the edge, and this edge is attached to an external edge. For example, I know P, but the degree of this node is not 3, is 2 or less, and the other is the same. Which, in other words, this condition imposes that the degree constraint must be 3. The other say that the network must be connected. Then the theory, I try to summarize the results of the theorem. It's not easy because it's 2 pages of results. But, well, anyway. Then we have this this model here. If WE is, as I told before, the continuous positive variables that represent the edge weight associated to the HE, then I can linearize the constraint x w greater or equal to d by introducing another variable. Well, this is trivial. I introduce another variable and I link the continuous part with the integral part. Xi, j, e represent the generic entry of the matrix, of the yellow matrix. And then I have the horrible constraint, I will tell you now because horrible. The anticycle constraint, which means I don't want matrix M1 and M2. I want the degree constraint, which means condition 2, and also the third constraint, which means that my network must be connected. This model, as you can see, has a polynomial number of variables, a polynomial continuous variable, a polynomial number of continuous polynomial number of continuous variables, polynomial number of continuous binary constraint, and well, it is relatively nice. But the problem is that this we have the XOR constraints that are really horrible. This is a sort of 5 pyramids in which the internal point, in which the extreme are in integer points, and when you try to relax, you fall inside these pyramids, and the relaxation is really poor. I have to jump. It is possible to strengthen the model by a Fourier Motzing approach. Anyway, there are many other models that we can build. For example, a flow-based model, a fixed tree model. This is interesting, for example, for people also working not only in mean evolution but also in with maximum likelihood or whatever. If you imagine that tree isomorphism is easy. We have an oracle. Graph isomorphism, we don't know where it is. Maybe it is in NP, but not NP complete, neither nor in P. But I can imagine to enumerate all the possible non-isomorphic tree shape whose number increase is exponential, but increase very slowly with respect to the number of all the possible topologies from a fixed number n. And then I can imagine that I want to assign the taxa to the leaf, so that, for example, my objective function is maximized or minimized. For example, in my case, I want to minimize the length of the tree, so I have to solve a quadratic problem in which I assign. Or, for example, I want to assign my taxa to the leaf so that the maximum likelihood is greater. So I don't have time. Well, let's go to the computational result, and then if there are some questions, I show just an example. Currently, as I told you, I cannot solve more than 12 taxa. Why? Because well, this is I show you the model. For example, I want to minimize the sum of, you see, this is the sum of the E in E. I define an edge set E. I want to minimize the variable. These are the variable continuous variable. I want to minimize that with the condition that for all for example, the acyclic constraint, for example, the XOR constraint, or for example, I want the variable of binary, and so on. I want to I try to, oh, you can see, well, if you see when I run the model, the optimization model, the number of node expanded in my branch and bound is huge. But the structure is really something strange, because there is some symmetry, and actually there are a lot of symmetry in my model. I'm unable to break this symmetry because there are some partial topology that whose sub length is similar to other partial topology. For example, well, okay. In another episode, I will tell you what happened. Okay.
Any questions can be taken outside.